Hello students, today we're going to learn section 1.2, functions and their properties. Alright, domain, think x values, and possible restrictions occur when a variable is in a radical or in the denominator. Range, think of your y values. Check graph for restrictions. So one more time, domain, x values, range, y values. Alright, a relation is a set of ordered pairs. A function is a relation where the x values do not repeat. So for example, all of these graphs are relations because they are a set of ordered pairs. Set of ordered pairs are points. So there are points throughout all this graph. Okay. So all of these are called relations. Now we just have to check which one is a function. So by using a vertical line test, you can check whether the relation is a function. If the vertical line crosses the graph twice or more, then it is not a function. So if we draw a vertical line, this is a function, this is not a function, because it will cross the graph two times, here and here. This is not a function because it crosses twice. This is a function because it only intersects the graph one time. So function, not a function, not a function, function. Continuity is where the function does not have any breaks, i.e. any vertical asymptotes or holes, which are also called removable discontinuities. And we'll go more into depth with this in section 1.4. And behavior, how the function behaves on the left end and right end. Again, we'll go more into depth in section 1.4. So example 1. They want us to find the domain and range in interval notation. So to find the domain and range for part A, we have to check, is there a radical or is there a variable in the denominator? There's actually a variable in the radical. So we know that in order for us to get real numbers, the value inside the radical has to be greater than or equal to 0. So D for domain, you take whatever's in the radical and it has to be greater than or equal to 0. So we get x by itself. So the domain is x greater than or equal to -3. They want the answer in interval notation. So what we have to do is, here's interval notation. Bracket on -3 and parentheses around infinity. Alright, so now to find the range, think of the y values. So let's put in y equals second square root of x plus 3. Hit the arrow so you're out. So this is the graph of y equals the square root of x plus 3. So the range, we think of y values, the y-axis runs up and down. So the graph of this function is above the x-axis. That means the range is going to be from 0. This is 0. There's 1. There's let's see, probably 2. So you notice that as this is continuing to go upward, the range, think of y values, it's from 0 and continues upward. Because this function continues upwards, that means the y values are also being used. If you want to look at the table look at, let's see, table. So we know that, think of the y values. Here are all the y values. Okay, so it continues. Now if we look at the domain, let's see, we said greater than -3. So here are all the x values. Now look, if we go to -4, what's going to happen? There's an error. Because once you have -4 in here, you're going to have the square root of a negative number, then it's imaginary. Alright, let's look at part B. Part B is g of x equals the square root of x over x minus 5. So the domain, we're going to look in two areas. We're going to look inside the radical because there's a variable in the radical. So we know anything in this radical has to be greater than or equal to 0. So x greater than or equal to 0. And we know the denominator cannot equal 0 because if the denominator equaled 0, we'd have undefined. So we take this denominator not equal to 0. So x cannot equal 5, and x has to be greater than or equal to 0. So now to write the domain in interval notation, it's from 0 to 5, union with 5 to infinity. So let's graph this. This is, we'll clear it. This is second, and that's x, go outside of the radical, divided by, put parentheses, x minus 5, close parentheses. We'll graph. So we notice that the range, think of y values, the range are all real numbers because the range is coming from -infinity to 0, and then it continues from 0. Let's say 0.001 all the way to positive infinity. So range, think up and down. So the range would be from -infinity to infinity. Alright, last one. H of x equals 2 over x. So we know the denominator cannot equal 0. So that means the domain is from -infinity to 0 because it cannot include 0, and union with 0 to infinity. So that covers everything. So here's the domain. Domain, think x values. It's coming from -infinity and it covers all the x values, and then it continues back up here, and then it continues to positive infinity. So the domain are all numbers except x cannot equal 0, because if x were equal to 0, this would be undefined. So that's why there's a parentheses around here. The range is also from -infinity to 0, union with 0 to infinity. So range, think up and down. So again, it's covering all the y values, but not 0. Alright, this would be a vertical asymptote. So we talked earlier about continuity. This function is not continuous because there's a discontinuity at x equals 0. There's a vertical asymptote here. There's a break in the graph. Okay. Next concept is, it says for each graph, identify the local max, local min, intervals on which that function is increasing, decreasing, and boundedness. So let's just go over the first one. So if we look at this graph here, this is a function. It passes the vertical line test. So now what we're going to do is to find the local max, local min. The local max is where you have a change of the direction. You have a change of increase to decrease. So this is a local max. This is a local max. This is a local minimum. So local max, the point is -4,3, 2, 2. Local minimum, change from decrease to increase. There's a change here that's going on, and that is your local minimum. In calculus, we call these critical points. Okay, so the next is identify the interval of increasing, decreasing. So when you look at intervals of increasing, decreasing, think x values. So from negative infinity, it's increasing all the way up to negative 4. So again, as this arrow means it continues going downward this way, we're catching all the negative numbers to the left. So negative infinity, and then it goes to negative 4. It's decreasing from negative 4 to negative 2. So when we look at increasing, decreasing of a function, think x values. From negative 2 to positive 2, it's increasing, and from 2 to positive infinity. Not negative infinity, it's positive infinity, because as we continue this way, the x values are increasing. So these are the intervals of increase, decrease. Again, think x values. Last thing is check boundedness. This function is bounded above, meaning there's a ceiling here. There's a cap. So it's bounded above. There is no, it's not bounded below, because these arrows mean it continues to go lower and lower. There is no floor. So this is bounded above because it has a ceiling. Alright, next, part B. Part B is, here's our next, notice there's no arrows here. So local max would be negative 3, 3, 2, 2. Local min would be negative 1, 5, negative 2. Those are local min. So it's increasing negative infinity to negative 3, decreasing negative 3 to negative 1, increasing negative 1 to 2, decreasing 2 to 5. Remember, think x values. And increasing from 5 to 6, because that x value is 6. Here, this is bounded. It's bounded because it has a ceiling and it has a floor. It has a ceiling and a floor. So it's bounded because it's bounded above and bounded below. Next topic, we're going to talk about even odd functions. To determine whether a function is even or odd, what you're going to do is you're going to substitute negative x wherever you see an x. When you substitute negative x wherever you see an x in the function, if you get the exact same function, it's even. When you substitute negative x for x and you get the exact opposite, it's an odd function. If neither of these two occur, then it's neither. So example 3, determine if the function is odd, even, or neither. Well, here is f of x equals x squared minus 3. Substitute negative x wherever you see an x. Negative x squared is x squared. Now, this is the exact same value as that. Therefore, when we substitute negative x in for x, we get the exact same function. So f of negative x equals f of x, therefore f of x is even. Alright, next we have h of x equals x cubed over 4 minus x squared. Again, substitute negative x wherever we see an x. Evaluate it. So negative x to the third power is negative x cubed. Negative x squared is positive x squared. Bring down the 4, bring down the minus. So what we have is we have the exact opposite, because this is negative of x cubed minus 4 over x squared. I'm sorry, x cubed over 4 minus x squared. So this is the opposite of the original function. So if you have the exact opposite, what happens is you have an odd function. Okay, that's it. Thank you.